In this video, I'm going to summarize the major parts of the Force on a Particle Model, or FPM. So the first diagram that we used as part of this Force on a Particle Model is the interaction diagram. The interaction diagram tells us three things. It tells us what objects are interacting. It tells you what type of interaction each of those are. And it tells you what the system is. So if I do this for a block on a ramp, for example, the objects that are interacting, I've got the block, I've got the ramp, and then I have the earth. Everything in these bubbles should be specific objects, so things you could physically point to or touch. So that's why I put Earth in that bubble and not gravity, because the Earth is the object that the block is interacting with. And then the type of interaction is the force of gravity. There will for sure be a normal force interaction between the block and the ramp. That's where those atoms are compressing each other. And then I'm going to go ahead and say this is a rough ramp, so it's got a nice rough surface, and there's some force of friction. At this point, the interaction diagram does give a good illustration of Newton's third law, which says that if you have a single interaction, it exerts the same force on both objects. I have this visual that there's just one interaction between the block and the earth, which is that reminder that the force the earth exerts on the block is the same as the force the block exerts on the earth. The last thing I do on my interaction diagram is I define my system. I can put as many or as few objects into my system as I want for the problem, and what makes the most sense just depends on what I'm trying to find out. In this case, I decided to put just the block in my system. Alright, sorry, I forgot to silence my phone. The next type of diagram we use is the free body diagram. This is also sometimes called a force diagram because it shows the direction and the relative size of the forces acting on an object. And we often call this just an FBD. Now with something like a block on a ramp, I find it really helpful to just sketch in the surface of the ramp. And then the free body diagram, that's where I shrink my system down to a single dot. So that dot would represent the block. And then I need an arrow for each force that's external to the system. So each interaction with something from outside the system. And so I have the force of gravity. And that is the earth acting on the block. I have the force of friction, which would be pointing straight up the block. Or, I'm sorry, straight up the ramp. And that interaction is the ramp on the block. And then the last interaction I have is the normal force. And that is also the ramp on the block. The two big things that this bit in parentheses accomplish in terms of supporting your thinking. One, if you're taking the time to add those, it keeps you from adding forces that shouldn't be there. For example, when dealing with central net force, it's really common for people to want to include a force pushing the object outward to keep it on that circular path. So for example, if you have something that if you imagine a car going around a curved turn, to imagine a force pushing that car outward. The trick is there's not actually an interaction that's pushing the car outward. There's no object that has an interaction going in that direction. And so thinking about what has to be interacting can keep you from adding those forces that aren't there. The bit in parentheses is also useful for Newton's third law. If you have forces on two objects that have the same things listed in the parentheses. So for example, if I drew an FBD for the Earth, I would have a force of gravity of the block on the Earth, and that's a cue that those are going to have the same size of the force. And then, last but not least, the final diagram we had was the vector addition diagram. Or VAD for short. This is the diagram that is the forces from the free body diagram rearranged. And so, if I were to imagine, usually I start with my force of gravity. And then I would pick one of those other forces, either the force of friction or the normal force, and I would imagine it sliding it around. So it's still pointed in the same direction, but I'm going to start that arrow where I ended my force of gravity arrow. And then I'm going to do the same thing with my normal force. And then I would use some geometry to figure out where the angle of that ramp goes. Now with the way I drew this, it makes a closed shape, which means the forces are balanced. And as long as you have balanced forces, the object is going to move with a constant velocity. So if it already has some speed to it, it's going to keep going at that same speed and in the same direction. If it's at rest, it'll just stay at rest. Now, if my force of friction were a bit less, my normal force wouldn't change. But if I had less force of friction so that it wasn't enough to take up this full side of the triangle, then I would have some net force. This would be unbalanced. And then the arrow for the net force goes backwards, because if I think about when this block is sitting on the ramp, if the forces are unbalanced, I expect them to be unbalanced down the ramp. If this block is able to just slide, it's going to pick up speed as it goes down the ramp. So there must be a net force down the ramp. And so that gap in your vector addition diagram is the net force, which is essentially a measure of how unbalanced the forces are. And the net force is always in the same direction as the acceleration. It's not necessarily in the same direction as the motion. If the object were moving up the ramp and had a net force down the ramp, it would just slow down. So can be either in the same direction or opposed to the motion, but it's always in the same direction as the acceleration. And so what we'd do from here, if we were going to actually do a problem, is we would start solving for some of these forces, and once we got at least one force and that angle, then we could use some trigonometry and some geometry to figure out the other forces. There's also a few questions or a few equations on your formula sheet for finding the value of some specific forces. We have Newton's second law, which gives us the relationship between force and acceleration. And then we have an equation for the force of friction, an equation for the force exerted by a spring, which depends on the stiffness of the spring, which is described by this little k. And then x describes how much that spring is either stretched or compressed. And then this last equation gives us the force of gravity. So we'd use these to put some numbers to sides of the triangle, and then we would use geometry and trigonometry to work through and figure out the remaining sides to work towards whatever it is we were looking for in the problem.